Okay, today will be the most and last topic, most theoretical and last topic before the midterm. Okay, it will span a couple of classes. Okay, because it's quite theoretical and I want to explain things in quite uh, a detailed manner. Okay, to this end. Okay. This is about queuing theory, right? Have you heard of queuing theory? Uh, what do you think it is about? It's about the study of queuing, right? Uh, the use of queuing theory to study the queues in packet switch network is just one application, but the underlying study is much more general. Okay, so basically, as the name says, okay, it's just a study of a system consisting of queues, right? And other than packet queues, what other you've encountered queues in everyday life, right? What is your primary physical example? Like if you go to a cafe, right? Then your orders are queued, right? Oftentimes, for example, you go to Amazon Cafe. Most likely when you go in, you're not alone, right? Some customers are already being served, right? And you as a newcomer, okay, you have to come in where in the queue, at the back of the queue, right? Right. So you typically, when you arrive, right, you are the latest customer, right? And depending on how large the system is, okay, um, if it's a very small system, okay, there's only one service worker. So in the case of Amazon Cafe in the faculty, as you can see, there's only one counter, right? So there is only one counter to receive your order, right? And of course, the customers that are coming in will be queue, right? Because there is only one service counter, okay? In this simple case, one queue is enough, right? And of course, the most natural queue, okay, that you can think of is what type of queue? First come, first serve, right? Or first in, first out, okay? The earliest customer that arrives should be the first one to be served, right? So when one customer, um, when is the time for the customer at the head of the queue to be served, what will happen? So right now, let's say this customer is being serviced, right? This customer is being serviced. One second. This customer with the red cap is now being serviced, right? Uh, yeah, right. Okay, one second. This customer is being serviced, right? There are three left in the queue, right? In that order, right? So what will happen at the moment where this customer or customer's order is completely serviced? He will get, he or she will get the coffee, right? And basically, he or she will leave the system, right? At that moment, what will happen to the queue? What will happen to the queue? At that particular moment where there is one customer leaving the queue, sorry, leaving the service counter, then what will happen to the queue? The one at the head of the queue, right? Will be the next guy to be serviced, right? And so the queue will shrink by one customer, right? And this person will become the next head of the queue, right? And this process will continue, right? Throughout uh, the life of the system, right? Okay. So as you can imagine, okay, that is just a canonical example of a very simple queuing system, right? But when we develop systematic understanding of queuing systems, okay, you will realize that it's quite general and you can apply it to wide-ranging um, engineering case and non-engineering cases. Something like call center, right? You have operators, right? Potentially many of them, right? Working for a call center, receiving customer calls, right? So this is a more complex situation, right? With potentially many operators, each of them having his or her own queue, right? So in this situation, depending on how large the call center is, right? There may be a huge number of incoming customers, right? Per period of time, and they have to be split into multiple operators depending on their availabilities, right? And in that sense, different calls will be queued up into different queues belonging to different operators, right? Another example you see almost every week is at the retail stores, right? Something like grocery or something like a grocery store or supermarkets, right? So here, the uh, entities that are queue are shoppers, right? And the servicer are the cashiers, right? And the queues are the checkout lines, right? And of course, a primary example, most relevant, I would say, to this course is the queues for a packet switching network, right? Like the internet, right? Where the entities that are queue are incoming packets, right? To, let's say, a router, right? With a queue, right? And so the servicer in this case is the process of forwarding in the router, right? So in this case, a router can route different packets to different outgoing links, right, from the router, right? Other physical examples are queues for transportation, right? At bus stations or train stations, right? So you see examples everywhere, right? Right before you come to this class, you are queued up at the faculty cafeteria most likely, right? As you can see, there are wide-ranging types of applications, and I think I could convince you enough that, okay, um, with your knowledge, good, solid knowledge of queuing theory, then you can use it to analyze and engineer a lot of important systems, right? So going back to this very simple picture, okay. If I want to break the queuing system down into essential elements, what would you think should be the first element of the queuing system? How many parts are there in this picture in a queuing system? Remember when I talk about a system, right? So it's this whole thing, right? Because different parts interact, right? Because if you have more customers coming in, right? Of course, the queue will grow, right? On the other hand, if the servicer is quicker to service coming customers in the queue, then the queues can be depleted more frequently as a consequence. Okay, even though there are so many incoming customers, if the servicer is so quick, then the queue size on average would not grow too much, right? So having said that, what do you think should be the first essential element of a queuing system that we should consider? You don't have to give me such a specific word. You can describe what I should study first. System is about input and output, right? So where is the input in this case, in the queuing system? How customers are arriving, right? On the left, right? Because that's, you can think of it as an input, right? Of course, the internal of the system is about the queue and also the servicer, right? And the servicer and both of them will determine the output, right? Along with the input, right? The output will depend on the input. But now the first thing that we should consider is the input, right? Or to put it differently, we should consider how the entities that are being queued are arriving, right? The formal term for that is in queuing system is what we call the specification and determination of the arrival process, right? The keyword here is a process, right? When we talk about process, right? It's not just variable, right? Process signifies that the uh, subject under study is a function of time, right? Because here you want to study how different customers are arriving as a function of time, right? Correct? Um, and as you can imagine, there will be many aspects to this, right? Because there could be wide-ranging situations where customers are arriving in different fashions, right? For example, for some queuing systems, you rarely see individual customers, right? Customers would come in group. What type of situation can you imagine group arrivals? Pardon? Burst? Sorry, burst? Uh, make it realistic. Like what type of place would have bulk arrival? In which place you rarely see customers coming individually? Yeah, something like theme park, right? They come in families, right? Oh, yeah, pardon? Theater? Yeah, maybe theater. But some people, many people are going to the theater alone. But I would say you can contrast it to something like a cafe, right? Where many people will go there alone. Okay. So here is only one aspect, right? But of course, if you want the full detail of this arrival process, you need to specify this entire process as a function of time, right? And we all know that in communication, okay, the way to model uncertainty is to look at the process in terms of probability, right? So you have to uh, uh, specify the distribution of these arrival, right, as a function of time, right? How do you do that? Okay. For example, let's make it the simple case of all individual arrivals. Then how can you specify this arrival process probabilistically in a complete manner? Let's say if you plot it on a graph as a function of time, right? Okay. How can I describe the entire arrival process probabilistically? So then if this is the starting time, right? Let's say first customer arrive here, then maybe later on second customer, third customer, and then fourth, fifth. How do I specify these different times? There could be many ways, right? But one way I would argue that uh, can be used to specify the entire process is you can look at the distribution of the so-called inter-arrival time, right? So this time from start to the first time when the customer arrive, first customer arrive. This the second time between the first and the second, and second and the third, respectively, right? This will be T4, right? And this will be T5. Of course, because we allow for uncertainty, all these times are random variables, right? So in order to specify them, okay, you need to specify their full distribution, right? And for example, it will be the case for the canonical arrival process called Poisson arrival, where customers are arriving individually, independently. You will see that all these times, okay, inter-arrival times can be modeled as mutually independent, right? So that means it's enough to just know the marginal distributions of these inter-arrival times, right? And because of mutual independence, you can just multiply them up to get the joint distribution, right? And that's how you get the full distribution of the entire process as a function of time, right? Another thing that you you will need to consider is the size of the population of incoming customers, right? Okay. Um, uh, in many queuing system, okay, it can be intuitive to assume that the size of this pool is very large, and you can approximate it as infinite, right? Something like a cafe, right? Amazon Cafe. What do you think will be in the faculty? What do you think will be the size of the pool? We don't know for sure, right? But definitely should be no larger than population of Thailand, let's say, right? Or maybe the population of the world, right? So that's very large compared to the system. Then you can assume it to be infinite, right? But for other situations, this pool size is finite, okay? And that's when you have to take it into account as well, okay? So maybe having talked about the arrival process, right? It'd be instructive to think about, okay, the most simplest arrival process you can think of. What do you think it is? Okay. something like a completely deterministic arrival, right? At completely regular intervals, right? So then you just specify the inter-arrival time period, right? And then de depending on how long the system progresses, then you can divide by this period to figure out how many customers have arrived, right? But in realistic situation, that's rarely the case because having such a deterministic uh, arrival process means all the incoming customers will have to coordinate themselves, right? To come at such regular intervals. But in realistic situation, that will rarely be the case, right? Okay, widely used and also quite realistic model for typical uh, arrival process, okay, involving virtually infinite number of customers, okay, working independently, okay, uh, to arrive, right, is what we call the Poisson arrival process, right? Have you heard of a Poisson arrival process? You heard of Poisson distribution, right? From probability and statistics, right? What do you recall of the Poisson random variable? Poisson, discrete or continuous? Continuous. When you learn about it, there's a discrete version as well, right? But here, because we talk about time periods, okay, it's closer to the uh, continuous one. But in fact, we will use the discrete one as well. Okay, so this arrival process is quite important because it represents an arrival process in realistic situation involving the following assumptions, right? One is that the pool size, remember, virtually all potential customers that can come in can be considered to be basically infinite, right? Something like a cafe that I talk about, right? So the pool size is very large compared to the system, right? And as a consequence, okay, because of that, for a Poisson arrival process to be feasible, the impact of an individual customer should be insignificant, right? So it's only the aggregate of all customers that are coming in that will matter, right? But each one will will use the system resource very insignificantly. Okay. And the third one is very important that the customers do not collude, right? They act on their own. They come and go independently of one another. They don't know one another. Okay, their decisions to use the systems are independent of one another, right? Another canonical example of system in which the arrival process can be considered Poisson is something like a section of the road or a highway with cars coming in, right? As you can see here, if for a considerably long section of a highway, right? Each car will be occupying only insignificant resource, right? Or the road section, right? To itself, right? And so many cars are coming in, right? And in almost all situations, the cars are coming in independently, right? They don't come with one another in the form of a caravan or something like that, right? And in addition to that, the total number of potential cars, okay, that can come into the highway can be considered to be very, very large, right? And as I said, they act independently. Their decisions to enter the highway are independent of one another's, right? Except for very rare situations, something like a car rally, right? In which they form a caravan and come in together, right? But in typical situation, okay, the cars that are coming in are acting almost always independently, right? Okay, other feasible example to model the arrival process as Posong is something like a call center, right? Because uh, there could be so many calls coming in, right? From potentially very large pool of customers. Each customer's call uh, can will occupy only a small fraction of time of the operator, okay? And calls, they are coming in independently, of course, because by definition, a call is individual, right? You cannot combine many calls and have them come in together at the same time, right? Okay, let me remind you of the Poisson random variable again. So you see it in this picture. Okay, now are you reminded of the Poisson distribution now? So which random variable is Poissonly distributed in this formula? What should be the definition of this? Remember, process is a function of time, right? So this capital N as a function of time, what should it represent? Number of entities, right, that are coming in as a function of time, right? So if little t is larger, what would you expect to happen to n of t? If if the t, right, t is the interval under consideration, right, 0 to t, right? And nt here should represent the number probability of uh, all customers, let's say, coming in during this period, right? So if t is larger and larger, what would you expect to happen to n of t? Should have a larger distribution, right? Mean should be larger, right? Accordingly. So now do you recall the formula for Poisson PMF? You can refresh your knowledge. You can just Google and see if you recall. So which one is Poissonly, which random variable in here is Poissonly distributed? Little k, remember the notation? Little character for deterministic value, right? Random uh, variable is represented by capital letter, right? Remember? Which quantity is capitalized here? K is little k, right? K is the value, right? Of N of T. N of T is Poissonly distributed, right? Remember, this is a PMF, Poisson is a PMF, meaning this random variable is taking values as integers, right? And the Poisson distribution or Poisson PMF is basically a class of distribution, right? Parameterized distribution. So what should be the parameter of N of T here that is Poissonly distributed? Pardon? T is the parameter of N, right? But I'm talking about NT. What should be the, we already argued that, okay, the form fits the Poisson PMFs, right? But the Poisson PMF is parameterized, right? It can take many parameters. So which parameter value in particular is the Poisson PMF of N of T? Where can you find it in this formula? Huh? Lambda? So you said this, right? So, right? So then just look it up in Google maybe. What is the formula for Poisson PMF with the parameter lambda? Do you see that? Poisson PMF with parameter lambda. What should be the formula for the PMF? E to the negative lambda. In this case, the running value, right? K and K factorial, right? But does it match here on the right? So what should be the parameter? Lambda T, right? So what do you think lambda T is? We already mentioned what T is, right? T is the time duration under consideration, right? The larger T is, the more customers are arriving during this period, right? And that will determine the parameter of the resulting Poisson distribution. So what do you think lambda should represent? The larger the lambda is, how does this parameter relates to the Poisson random variable? This is the parameter of the Poisson random variable, right? For example, what is the mean of a Poisson PMF with respect to the parameter? What is the mean of the Poisson PMF with respect to its parameter? Mean, do you know what mean is? Expectation, right? Mean is you already told me this is a formula for the Poisson PMF, right? For this distribute with parameter lambda, let's say, what is the mean of this? So this one, actually the mean is lambda, right? But because here we have lambda T, right? So the mean for N of T is lambda T, right? So what do you think lambda should represent then? Notice how this mean scale with T, okay? So let's say you increase T twice, what should happen to the mean of NT? Yeah, so it's go up linearly, right? So then what should represent lambda? Rate, right? So it should be the rate determining how frequent each customer is coming in on average, right? So in this case, could be customer or package, right? Per second, right? The real unit for the incoming entities can depend on the situation, but the denominator should be in second, right? Clear? So this precisely why we call this arrival process per song, because if you consider the resulting n of t, then it turns out that it is a Poisson PMF with parameter lambda t, where lambda is the so-called arrival rate, right? In terms of customer per second, right? And for a fixed arrival process, you fix lambda, okay? So this mean of the number of customers arriving within time period t will scale linearly with t, right? Makes sense, right? If this has a unit of customer per second and you consider 10 seconds, right? On average, should be 10 lambda, right? Right? Make sense? Are you recall of Poisson PMF? Okay. So that's what it is. Okay. Lambda is the average arrival rate, right? And because once you define the Poisson arrival process, right, then you can define this n of t for any t, right, and any k. So basically, you can describe the entire arrival process fully, right? What else should you describe for the Poisson arrival process? In the first example that I show you about customer arriving, what did I consider? Other than the number of customers that have arrived in a certain duration, what else did I consider earlier when I draw the arrival diagram? Remember T1, T2, right? That is what's so-called the inter-arrival time, right? So let's say I describe arriving customers in this arrival diagram, right? For a regular arrival, it will be something like that. But for a more realistic system like a Poisson arrival, the arrival instances would be more random, like something like that, right? And then you can consider the so-called inter-arrival times, right? And these are the length of the time differences between consecutive arrivals, right? So with the description of the Poisson process that I have described, okay, what do you think should be the distribution of the inter-arrival times for the Poisson arrival? What should be their distributions? T1, T2. What do you think should be the distribution of the inter-arrival times for the Poisson arrival, given the description of the Poisson arrival that I told you, right? That It is to represent independent customers arriving, right? Let's say it's a Poisson arrival process of rate lambda, right? Customer per second, whose distribution for n of t that you already know, right? Now, I want to use that to derive the distribution of inter-arrival times. The question I ask is, what type of distribution should these different inter-arrival times be? What do you think? They need to mutually independent, not just independent. Mutually, it means all of them are independent. Okay. So why do you think all the T should be mutually independent? Just maybe described by your intuition. So let's say T1, right? What do you mean by T2 is independent of T1? Yeah, but by saying that, let's just consider two, right? T1 and T2. Why should T2 be independent of T1? How can I argue that T2 is independent of T1? What is the concept of independent about? Concept of independent of, let's say, two random variable means, had I known the value of one, it does not affect my probabilistic knowledge of the other, right? So in this case, it's like having known T1 is like you already know that eh? How come I cannot? 1 second. Okay, having known T1 is like I already know that. Okay, this is the starting point. This is the first customer, right? I already know the value of T1, right? Okay. Assuming that I know the distribution of T2, should my knowledge on T1 affect the probabilistic knowledge of T2? No, right? Because T2 is about 2 and 3, but customer 3 is independent of the first two, right? In the Poisson arrival process. And similarly, for the subsequent T's, right? Okay, so mutually independence should be the first thing that simplifies things a lot, right? Because remember, if you know that the variables are mutually independent, you just need to find their marginal distributions, right? Because the joint distribution will just be the product, right? So what's the second thing that you should be able to say about the marginal distributions of subsequent T's? Let's say T1 and T2. What is the other thing I should be able to say about their marginal distributions? Before exponential. If you already know by going to the next slide that it's exponential, but even before the exponential, what should I be able to assume about the marginal distribution of subsequent T's? Okay, let's make it simpler. Okay, let's say if I talk, let's say this is the first customer, okay, this is the second customer, to forget ourselves about the origin, right? Because the origin may not be the arrival time of any customer. Let's say I already know the marginal distribution of T1, and I already know the marginal distribution of T2. Then what should I be able to say about the marginal of T3, marginal distribution of T3 with respect to T1 and T2? Okay, maybe even going back, let's say I know the marginal distribution of T1. What should I be able to say about marginal distribution of T2? with respect to T1. So if you consider T1, right, it's like considering how late the second customer should arrive after the first customer, right? If I know that distribution, then I know the marginal distribution of T1. What about T2? Let's say this is the first customer, this is the second customer, this is the third customer. Verbally, what is T2 about in terms of distribution? It's about T2 is about probabilistically how late customer 3 arrived in relation to customer 2, right? Right? That's all I care about, right? If I know that probabilistically, I can use it to derive T2, right? And then what about T1? T1, I just replace 2 with 3 with 2, and this is 1, right? So then what should I be able to conclude about T1 and T2 for the Poisson arrival process? For the Poisson arrival process, all customers act the same manner, right? They come in with the same rate. So it should not matter whether I consider the pair of customer 3 or 2 or 2 or 1, right? Probabilistically, it should be the same. So what can I conclude from this? T2 should be marginal of T2, marginal distribution of T2 should be exactly the same as the marginal distribution of T1, and that they should be independent, right? So knowing that T1 and T2 are identically distributed and they're independent with the same assumption of customers being probabilistically identical and act independently, having known the marginal distribution of T1, T2, what should I be able to claim about T3? Again, the same, right? Except that it is independent of T1, T2. Similarly for T4, T5, and so on. So in order to know the joint distribution, the only thing I need to do is to derive this marginal distribution, right? Which is identical, right? And I think this calls for a break. Maybe you think of it a little bit before I can convince you the exact form of this marginal distribution of the inter-arrival time for the Poisson arrival process. Okay? Okay, maybe breaking. I think I have convinced you enough that for the Poisson arrival process, right? Let's say with parameter lambda, lambda, lam, eh? Lambda, eh? How come? Oh, okay. Maybe I didn't turn it on. Okay. With the arrival process, lambda, let's say customer per second, right? Or any lambda, right? For any lambda, the inter-arrival times, okay, as random variables should be mutually independent, right? And the marginal distribution of each of them should be identically distributed, right? Then the question is, what is that marginal distribution as a function of lambda? Okay. It has to be a continuous distribution, right? Because all the t's are continuous, right? Or the PDF, right? And first of all, let me ask, what should be the mean of this marginal distribution? That should be the first question to come to your mind, right? As a function of lambda. Lambda is describing how frequent, right, the customers are coming in, right? Because the larger the lambda, the more customers are coming in per second, right? If I know lambda, what should be the average of the inter-arrival time distribution? It's a very straightforward question. What is the unit of lambda? Arrival per second, right? But what should be the unit of t? Second. So then what should be the mean of t for each t? What is k? Should only be a function of lambda, right? Let's say I know lambda, right? Let's say I look at the system for 10 seconds, right? Right, then what should be the average number of customer in 10 seconds? Is 10 lambda, right? So that means on average there are 10 lambda t's, right? T1 to T10 lambda. Then what should be the size of each t? So each t should have a mean of what as a function of lambda? They are the same, right? So why not 1 over lambda, right? Because if it's 1 over lambda, if I know that each customer should take 1 over lambda, right? Then if I, so this is in second, right? Then what can I say? This is roughly saying that one customer is coming in every 1 over lambda second, right? On average. So then what should be the incoming rate? Saying this means that roughly speaking, on average, one customer is coming in every 1 over lambda second, right? One customer is coming in every 1 over lambda second. So what is the incoming rate? It's 1 over 1 over lambda, right? So that's lambda. So that should make sense, right? So by knowing lambda, knowing the description of the Poisson process, I should be able to verify that the mean of each inter-arrival time should be 1 over lambda. But that's not everything, right? Because I need to specify the distribution, right? So what form should the distribution take for the inter-arrival time? Okay, to that end, okay, I will zoom in, okay? Let's say this is the first customer, this is the second customer, right? I already know that they arrive at that time. Let's say I look into the future to specify the distribution of T2 according to the rule of the Poisson arrival process. Okay, so to that end, I can ask the following question. Let's say I know that T2 is larger than S. What do I mean by that? So this is the first customer, this is the second customer, right? Knowing T2 is larger than S means that after the second customer has arrived and I have wait for S second, if T2 is larger than S, what does that mean? That means after a second, third customer has not arrived, right? So at this point, third customer has not arrived. Knowing this, I can ask, how would that affect the future probability of T2 to be T second longer? Having wait for a second, what is the probability I have to wait longer than t to see the third customer? Okay. What do you think should be this conditional distribution? Having wait a second, what is the probability that I have to wait t second longer to see the next customer? Should be independent of s, right? Because of the nature of the process, right? Uh, the fact that I have not seen new customer for a certain period of time doesn't affect the incoming rate in the future. So they could still coming in at the same rate. So probabilistically, this should be the same as this distribution, right? And this is true for an arbitrary S. Do you recall what does this property mean from probability and statistics? This property that having wait a second doesn't affect the future distribution. Remember, t here is a variable, right? T here is a variable describing the entire distribution in the future, right? After I waited for a second. So this means that the knowledge of waited for already a second doesn't affect the distribution for the future for any t, right? Because this is independent of s, right? My question is, have you recall what type of property this distribution of T2 and hence every T should exhibit? This independent of little s is called memoryless, right? Have you heard of memoryless property? Okay. Memoryless. Okay, I switch S and T a little bit, but it's the same, right? So when I wrote it, it's S and T, here is T and S, okay? So the distribution, continuous distribution that satisfy this property is called memoryless, okay? What kind of distribution continuous PDF that you recall that would be memoryless and has mean 1 over lambda? What do you think that distribution should be? We know its mean should be 1 over lambda, right? And we also know it should be memoryless. Exponential, right? You all learn about this. Exponential, which is this type of this distribution. Okay. Now it's a PDF, right? Unlike Poisson PMF, right? It's PDF because each inter-arrival time is continuous, right? So that's the shape of the distribution, exponentially decaying, right? The larger lambda is, right? The smaller the mean of this exponential distribution, right? Because the more frequent customers are coming in, the shorter should be the mean of the inter-arrival time, right? Of each customer, right? And you can verify that this is indeed satisfy our intuition of memorylessness, right? Because of the form of the PDF, we can check the quantity on the left here to be exactly equal to the quantity on the right, regardless of T and S, right? So I think I convinced you enough that with a Poisson arrival process, right? The inter-arrival times, all the T's, should all be mutually independent and identically distributed And for a Poisson arrival process with arrival rate of lambda, in particular, each marginal distribution of the inter-arrival time should be exponentially distributed with the parameter lambda, right? Okay, any question, comments? I let you absorb the slides a little bit before I proceed. So as I said, I want to build a very solid foundation because you will need it to proceed. Any question, comments? I'm pretty sure you learn about memoryless in probability and statistics class, but back then you may not know the significance of it. Now you see one, right? Any question, comments? Okay. So now that we know all the inter-arrival times are identically and independently and exponentially distributed, right? With the same parameter, okay? You can use some byproduct of independent exponentially distributed random variables to say something, for example, about the minimum, right? If you have two independent exponentially distributed random variables with different parameters, right? You take the minimum, you can derive the distribution of the minimum, and you can see that it is also exponentially distributed with the sum of the mean, right? So now you can apply to Poisson arrival process. You take minimum of many inter-arrival times, right? That minimum will just also be exponentially distributed, right? With uh, the parameter being multiplicity of lambda, right? Depending on how many inter-arrival times you take the minimum. If it's 2, then it will be 2 lambda, right? If it's 3, it will be 3 lambda. If you take minimum of T1, T2, 3T, for example, then that minimum will be exponentially distributed with parameter 3 lambda. Right? Okay. So that completes our discussion of the arrival process, right? Which you may recall that it is only the first element of the queuing system, right? What is the other two elements of the queuing system? Is the queue and the way each customer is being serviced, right? So let's talk about the latter one first. That is what we call a service mechanism. Okay. This is about how individual customer is being serviced, right? So basically, you can completely describe it by find the distribution of the so-called service time, right? And ideally, right, and democratically, all the customers should be treated in the same manner, right? So then they should be subject to the same service time distribution. Okay, but there are other elements that could determine the nature of the service mechanism, because in more complicated queuing systems, as we have described, right, there could be more than one queues, right? And there could be multiple servers, right? So the number of servers have to be taken into account. Okay. Another important element is how the servers are interacting with the queues, right? For example, with many servers, they may have their own queues, right? Or in some situation, there could be only one queue and the servers are all serving this common queue, right? There are other spurious consideration that we need to take into account when you want to fully consider service mechanism, something like rare situation like preemption, whether it's allowed or not, okay? Or maybe some emergency situation where some customers whose requests are more urgent will be serviced first, okay? But for the typical situation, as I already mentioned, all customers should be treated democratically, okay? Subject to the same distribution, and typically no preemption is allowed, right? The first one that is coming in should be the first one that is going out, okay? So that's the service mechanism. The last element is the queue in the middle, right? Of course, the most natural one is first in, first out, or first come, first serve, right? But that's not the only possible flavor of the queue. In the direct opposite to that, what do you see? Last in, first out. What type of queue is that? Have you seen it? Stack, right? Right? And you use it in algorithm class, right? Or discrete structures. Or in some situation, maybe the the position in the queue do not matter at all, right? The server just pick one customer to serve in the queue randomly. Other queues, other flavors of the queue require some maybe side information, something like shortest processing time first. So this means that the server will have to know the service times of the customer in the queue ahead of the time, right? And then in that situation, it may be efficient to do the shortest one first, right? To deplete the queue in a quicker manner, right? In a more difficult situation, okay, different customers may have, as I already mentioned, different priorities, okay? And the idea is that the servicer will pick the customer in the queue with the highest priority to serve first, okay? If there are many customers with the same priority, okay, the one closer to the head of the queue can be picked before the ones that are later on in the queue. In addition to the way the servicer is picking the customers in the queue to serve, okay, the customer behaviors themselves can, in the queue, can affect the queuing system, right? One natural behavior that every intuitive person would do if you go into like a grocery stores, right? You see a lot of cashiers, right? Which one do you pick? You pick the one with the shortest, right? Okay. So, but this behavior of barking is a little different. It means that barking means if, let's say there's only one queue, right? And the customer that is coming in here can decide to leave the system entirely without being served, right? So uh, they just don't want to be served anymore because it's too long. They just leave the system. Okay, that's called barking. Reneging. Okay, we've seen this all the time, right? Especially in grocery store, right? In a grocery store or supermarket. What do I mean by reneging? Reneging means customer will go into the queue first, right? But if the wait is too long, he will leave, right? So that's different from barking. Barking, you have to decide at the outset to leave, but reneging means you can join first and wait for a certain period of time. Jockeying, you see this as well, okay? You go into one queue doesn't move, right? You jockey to the other queue. Okay, and realistic queues, okay? Something like queues in the routers, they all come with finite capacity, right? But um, for some idealistic situation, if the capacity is considerably large, we can assume that it's infinite. Okay. So those are three elements of any queuing system. And the idea is that if we describe all these three elements in a complete manner, right? Something like a full description of the arrival process in terms of the Poisson arrival process with the parameter lambda. If we describe the service mechanism fully as well, describe the queue fully as well, then we can fully describe the queuing system, right? And when we consider all of them in aggregate, right, then we should be able to measure important metrics related to the performance of a queuing system, right? A natural question you may ask is um, the average time that each customer should wait, right, before he or she is being served, right? Another related quantity is what is the average service time. So that's first bullet is about the averages, right? But if you want to ask more refined question, you can look at their probabilities, probability distributions, right? Another very important metric is average length of the queue, right? A more refined question is to look at the queue length in terms of probability distribution and ask what should be that probability distribution. Okay. Another important figure of merit is what we call utilization of a server. Okay. Because if no customers are coming in, right, the server can go idle, right? So the time that the server is useful is when it is servicing a customer, right? So what is the expected fraction of time during which the server is fully occupied, right? Okay, when we consider the queuing system, okay, there's a well-known notation that is used to describe the queuing system. Okay, this is not the full description because for certain situation you need to clarify, right? But at least this gives you the user and the researcher the idea about what type of queue we're talking about. And this consists of fully 5 elements, right? First one is for the arrival process. Second one is for the service mechanism. Third one is the number of servers. Fourth one is the capacity of the system, meaning the full size of the system. Okay, meaning that if the system is full and another customer that is coming in, then that customer has to be denied the service. Okay, so this is related to the queue, the capacity of the queue as well. Typically, if there's one server, then the capacity of the system is the capacity of the queue plus 1, right? Because there could be one customer being serviced and the rest are in the queue, right? System population, again, this related to the Poisson arrival process we talk about, right? That we can idealistically assume that the population size is infinite, right? So if the fourth and last numbers are not specified, then we can assume that they are infinite, right? For arrival and service mechanism, okay, we talk about very importantly memoryless distribution, right? For example, for the inter-arrival uh, Poisson, uh, for the inter-arrival time of a Poisson process, right? For the service mechanism, okay, if you consider the service time being distributed exponentially, is also memoryless, right? So in that case, A and S will be denoted by M for memoryless for exponential distribution for the inter-arrival time and service time distribution respectively. For other type of probabilistic inter-arrival process and service mechanism, okay, we will use G for general distribution. And if any of them is deterministic, we use D. So as I said, for all these notations, right, it's not a full description. For example, if it's exponentially distributed, you still need to specify the parameters, right? And of course, for general distribution, you still need to specify those distributions, right? But at least this notation will give you the nature of the different elements in the queuing system. Okay. So having said that, what do you think should be the first queuing system, real queuing system that we should consider? What should be the arrival process? Poisson, right? So if it's Poisson, first letter should be M, right? And also by similar nature of memoryless, the service distribution should also be, service time distribution should also be exponentially distributed, right? So that's M, M and M. And if a queuing system is simplest, is the situation with only one server, right? One server, that's the third character here. If we assume arrival process is Poisson, so by definition, the population size infinite, so we can omit, right? And idealistically, okay, for the simplest queue, okay, we can assume that there is no specific limit to the queue, okay? The queue can grow arbitrarily, okay? Okay, that should be the simplest queue that we can analyze rigorously. That's what we call MM1 queue. Okay. And we will do so shortly. But before I go there, okay, I want to introduce you to a fundamental first result, right? Related more generally to all queuing system, not just of particular type. And this is called the Little's formula. Have you heard of the Little's formula? Okay. So again, Little formula. Okay. Let me say what the Little formula is before I derive it for you. Okay. So this is a very simple Little formula. Okay. Where NT is the average number of customer in the system. Okay. So this means both in the queue and being serviced. Okay. Lambda, of course, is the arrival rate of the incoming customers, right? What is T? Remember, this is average number of customers, right? So if the incoming rate is lambda customer per second, then what should be T? T should be the average time each customer spend in the system, right? Because if that is the average time, okay, if I multiply by lambda, should be the average number of customer in the system, right? So heuristically, what does this little theorem says? So it says that if I fix the arrival rate to be lambda, right, then the larger E of n is, meaning the crowded the system is, okay, the longer each customer should be expected to spend in the system. Okay. So that's basically the idea, right? And that is quite intuitive. Okay. But Little's formula goes a little beyond that by fully describe this relationship as a linear uh, relation, okay, with the coefficient being the arrival rate. Okay. So you think the identity is believable or what? It's believable, right? At least the unit check out, right? But because it's true, right? We need to at least it's true, of course, but we need to derive it as well, right? How do you start deriving this identity? Okay. To that end, okay, I will. Oh, I forgot to clear. Okay, to that end, I will have to define uh, certain quantities related to the queuing system. Okay. And that has to do with, oh, sorry, two functions, right? As function of time, that is A of t, which is the staircase function, okay, describing customer arrivals as a function of time. And B is a similar staircase function, but is describing the departure. So it's like if this is a queuing system, AT is being recorded here, right, on the incoming, right? Whereas DT is being recorded here on the outgoing. Okay. So with this description, what can you say already about AT and DT? Which one should be larger? Pardon? Larger. No. AT, like if I say A10, right? A10 would be how many customers have arrived by 10 seconds, right? And D10 would be how many customers have left by 10 seconds. What do you think is larger? Arrival, right? Because if the number of departure cannot be larger than the number of arrivals, okay? So if I know AT is always larger than DT, what is the difference? There is NT, arrive and have not left. That's the number of customer in the system, right? At time T, right? And that will be the proxy variable that we will use to derive E of N in the little formula, okay? So let's look at some realization of AT and DT for a very simple queuing system, okay? Let's look at some important instances here, okay? So what happened at this instance? First instance, first customer arrived, right? First customer arrived, okay? When the first customer arrived, what can I say about the queue? How long is the queue? Huh? By what I said, how long means the queue size, the existing queue size, right? When the first customer arrived. Because no one else have arrived, queue is empty, right? So if the queue is empty, the first customer can go to be served directly, right? Right? So at this time, the system look like this. First customer arrived, right? Queue is empty. The servicer is here. When the first customer arrived, he or she went to be serviced immediately, right? Right? What is the second important instance in this plot? After the first instance, I only have to look at the instances where some staircases shift, right? The second time is, I would say here, what happened there? Another customer arrived, right? So what happened, second customer, let's say, what happened to the second customer when he or she arrived in relation to the first customer? First customer is not done yet, right? Because if the first customer is already done, he would have left, right? But as you can see, D is still 0 at this point in time, right? So that means one is still there. So if one is still there being serviced, what will happen to two? Has to be queued up, right? So two would have to be put at the head of the queue, right? So what is the third important instance here? Here, right? What happened then? First customer is done, right? First customer is done. First customer leaves, right? Second customer go to be serviced, right? Leave the queue to be serviced, right? That's happened at that instant. And then what else? if you progress along the time axis, third customer arrived, right? So what happened then? Third customer is queue up, right? Because second customer has not done yet, right? And you can see that this type of behavior will continue, right? For subsequent customers, okay? At some time, okay, maybe during this period, you see what is the NT during this period. During this period is 2, right? During this period is 1. What about during this period? What is N of T? Equal to, just look at the size of the staircases. The shaded period, what is the size of NT? NT is AT minus DT, remember? So it's 1, 2, 3, right? NT is equal to 3 in that period. What does it mean? NT is equal to 3. How many customers are there in the queue? Huh? NT is 3, 4. Remember, NT is both in the queue and being serviced, right? If NT is equal to 3, it means 2 are in the queue, 1 is being serviced, right? So 3 is 1 plus 2, right? Okay, what happened at this instant where AT is equal to DT for the first time after the start of the system? AT equals to DT. System is AT is equal to DT. Empty, right? All the customers have arrived, are serviced, have been serviced and left. So during this period, okay, system is empty. And as a consequence, the server is idle, right? He or she doesn't have to service anyone, okay? So what happened at the time when the system is empty? I would say it's like you reset the system, right? You reset the system, go back to the original time again, okay? And start from scratch, right? Okay. Any question, comments about these plots? Pretty intuitive, right? You can mark the arrival and departure instances by the arrow. Okay, again, having described the two important staircase plots, AT, DT, and their difference as NT, right? Remember? And having told you the little formula in terms of the average number of customers in the system and the average time each customer spend in the system. What do you think if we want to derive the little formula? Okay, don't believe everything I say, but I told you little formula too, but now I have to convince you. If I want to prove little formula, what should be the proxy of the left-hand side of little formula? If I want to compute this average, how could I start? Now I know that there's AT, DT, right? Then quantity that is related to the left-hand side here should be, we could start from the time average of NT, right? time average of NT, right? How does that look in terms of the plot? What is that average in terms of the plot? It's just the numerator is the area between the two curves, right? Because the difference is NT, right? So let's say I average until time T0, then 1 over T0 of NT time of T0 to T0 should be equal to shaded area divided by T0, right? Right? Correct? So, but remember, little formula relate average number of customer to the quantity on the right hand side, which is average time each customer spend in the system, right? So now that I know that the left hand side is related to this shaded area, now I have to start relating it to the different times different customers spend in the system, right? So how can I do that? T0 is just a number, right? So how can I relate the shaded area? How can I relate the shaded area to the times different customers spend in the system? So let's be more specific. What is the time the first customer spend in the system in this plot? How can I put it in the graph? If I want to determine T1, let's say, where is it in the plot? So it should be from the time when AT first increment to 1, right? Until the time DT first incremented to 1. So where is that in the plot? Is here, right? This area, right? What about T2? Again, same idea, right? Should be from the time when the red staircase plot increment from 1 to 2 or here, right? Right? Until the time dt increment from 1 to 2. So basically it's that length. But because the step size is 1, T2 times 1 is that area, right? Correct? Similarly for T3, 3, 4, 3, 5, 3, 6, right? And T7, right? And until this time T0, which is the horizon under consideration for the normalized integral, right? So if what can you observe if I sum up all these areas? T1, T2, T3, T4, T6, T7. What if I sum these areas? The sum is, again, the same area between the curve that I just did the integral with in the first place, right? So what can I say? I can say that this integral nt, right, is equal to sum over k equal to 1 to a of T0. By the time T0, 7 customers have arrived, right? And then I can say TK, right? Correct? because the left side is the area between the integral of area between red and blue curve, right? And I just convinced you that that vertical integration is also equal to the discrete horizontal sums, right, of different sub areas T1 to T7, right? So I get that identity, right? So now you can start to see similarity with little formula, right? Because this little formula says something about En and Et, right? We're not there yet because somehow the parameter lambda has to emerge, right? How would you do that? First of all, if you want to get the honest estimate of average number of customer, you need to normalize, right? So on the left side, you need to normalize by the time horizon, right? So you get 1 over T0. But on the right side, if you want to get to the average of time each customer spend in the system, you also need to normalize by what? Remember, this is the sum, right? If you want to normalize, by what quantity should you normalize? It's a sum over A of T0, right? So if I want to normalize to get the average, I should normalize by AT, right? But if I divide by AT, I have to multiply by AT0 to cancel, right? So now you get this part as the normalized sum of different times customers spend in the system, which is related to that average. You get this normalized integral representing the average number of customers in the system. But to make the equality, you also need to multiply by this quantity, okay, which is AT0 by T0. What is that quantity? AT0 by T0. What is AT0? Number of customers that have arrived in T0, right? Divided by T0, what is that? That's lambda, right? That should be on average lambda. So that in a sense, how you describe, how you can prove little formula. Here, of course, there's the so you need to take T0 to infinity, right? To get the full average. But basically, that's the idea. Right? So the nutshell of the proof is relate vertical integration, right, to horizontal sum, right? The vertical integration is related to expected number of customer in the system, right? The horizontal sum is related to expected time each customer spend in the system. The coefficient that need to be calibrated is related to the rate at which customer come in. Right? That is lambda. Correct? But the nutshell is that you can compute the area between the two curves in two ways. One vertical doing the integration of n of t, right? The other one is doing the splitting the area between the two curves into sum of different blocks, right? Each block is of height 1 and width being the time subsequent customers spend in the system, right? As a consequence, each rectangle box has area Ti, right? Then when you sum T of I, you sum over all times customers spend in the system, average that by the number of customers that have arrived, that will be related to average time each customer spend in the system. Okay. So that's what you get. Okay. Okay. This little formula is very, very general. Okay. It applies to uh, all queuing system with minor condition of stability. What do I mean by stability? Uh, stability means the quantities under consideration does not blow up, right? How can the quantity under consideration blow up? How can the quantity under consideration would blow up? For example, if the system size grow indefinitely as a function of time, right? Then both the system size and the queue size can blow up, right? But for a typical system where the queuing system is stable, you will see that if you look at a long period of time, there will be frequent occasions, there'll be recurring occasions that the queues, that the system become empty, right? So basically it's reset back to the origin, right? And because of that, you can make sure that all quantities under consideration will not blow up. And if the quantities under computation do not blow up, then you always get this relationship in the Little's formula. Okay. And it's quite general. Okay. It's about what coming in has to go out related to the rate of the incoming, right? So as you can see, even within one queuing system, Little formula can be applied to multiple parts of the system, okay, as we will describe in the subsequent lectures. If you want to see more detail of the proof, you can look at these slides where, so this is where I relate the integral, vertical integration to horizontal sum, right? And the sums are over the times different customers spend in the system. And then this lambda emerges by just as the renormalization factor, okay? And then naturally that renormalization factor will be converging to lambda, right? By definition, okay? And that will conclude our first theoretical result in queuing system. And it's quite important. So I want to stop here so that you have some time to think, okay? And because if I go over the first queue, that is MM1, I will not be able to finish, okay? So I want to stop here so that you have some time to go back and reabsorb everything, convince yourself that, okay, little formula should be true, right? Because we'll be applying it throughout the subsequent consideration of queuing system, okay? Okay, any question, comments? Yeah. It's just this quantity, right? This, that identity is called the little formula. Okay. So what will happen if, so this, I show you how little formula is derived, right? So basically by computing the integral, right, between the two curves, right? But when I do the averaging, right? When I do the averaging, so here when I do the averaging, I need to basically take the limit, right, of the horizon t going to infinity. Okay. What if you have an unstable system? What does it mean to have an unstable system? It means you have a system that is blowing up with time, right? A simple system like that is the system in which the incoming rate is so fast that the service mechanism cannot service it in time, right? So what do you think will happen for such a system? The quantity will blow up, right? N of t will blow up as a function of time. So even though I can describe it for a finite time, because I have to do averaging over long horizon, okay? If I take the limit t going to infinity, things will blow up and I cannot claim the quantity anymore. But for stable system for which things do not blow up, okay, you will see, if you look at a very long horizon, you will see that the system will come reset itself from time to time. And the resetting can be seen here, okay, when system is empty out, right? So if you look at a stable system for a long period of time, you will see this type of resetting from time to time, depending on the parameter of the system. The resetting can take a very long time, but if it's a stable system, this resetting should recur indefinitely in the future. And if you have such a system, all the integration, all the sum will be finite, right? And then if everything is finite, the quantity holds. So you get the little formula. Okay, when we talk about real queuing system, first real queuing system like MM1, I can tell you exactly when the system blows up, okay? And you can maybe guess already, right? For MM1 queuing system, so M is the first M is arrival, right? So with first M is the arrival process, right? So with parameter lambda, right? Second M is what? Service mechanism, right? Service mechanism is basically the exponential time distribution, right? Of the service time of each customer. Let's say that's exponentially distributed with parameter mu. Okay, remember lambda is customer per second, right? So what about this mu? How do you think it is related to the average service time? We just told you exponential distribution with parameter mu has mean what? 1 over mu, right? So what should be the unit of this mu? If this is second per customer, right? Each customer spend this many seconds, right, on average. So this is again customer per second, right? So it's telling you how fast, okay, if the customer keep coming to the servicer, how fast can the how many customer the servicer can service them per second, right? So when do you think what is the relationship of lambda and mu that will make the system blows up? Very intuitively. mu is, yeah. So when the rate of coming is faster than the rate at which the servicer can handle, right? So that means if you take a long enough time, the queue will blow up, system will blow up, everything will blow up. So you can't say anything about little formula because the quantity, all quantities under consideration are infinite, right? But for stable situation where lambda is less than mu, that's when, okay, the system will reset itself indefinitely, right? In the future, that's when all the integrations are well defined, okay? En will be finite, Et will be finite, right? And by little formula, En is equal to lambda Et, right? So for MM1 queuing system in particular, we derive all of them together. You know the exact formula as a function of lambda and mu, okay? Okay, any question, comments? Okay, if there is no question, I need to go, okay? So I will stop the recording